Dr. Holbrow Sr., would you like to introduce the speaker today?
Well, I think I'll try. I've known him for quite a long time, and since about 1985, I guess it would be. Anyway, he has this interesting combination of technology and music. I'll skip a lot of the early stuff, but he went to UMass Lowell, where he did a combination major in sound engineering, sound technology, and performance and piano. And then, by a kind of devious route, he ended up in the media lab at MIT, first as an intern with Todd Mackover, who runs the Opera of the Future, and then as a graduate student, where he's working on a PhD. And he has a lot to do with how software is affecting and may affect music in the future. I don't know if any of you saw the PBS series called Breaking Sound, which I found extremely interesting. It's a great lead up, I think, to what Charles is going to talk about today. Anyway, so here he is from his apartment on the MIT campus, where he is, among other things, a resident associate. Is that the right title? So guiding young students and telling them to keep their masks on, I presume. Yeah. Right. So over to you, Charles.
Thank you. That's a accurate description. So it's a treat to be here. I love to talk about these things, and I'll try and go not too long. I'm going to share my screen. I do recommend headphones if you have them. If you don't, that's totally fine. But some of the audio examples I'll play will be a little easier to hear if you're not listening on very small laptop speakers, for example. Like Charles H. Holbrow mentioned, I'm a PhD student at the MIT Media Lab, where I study with Professor Todd Mackover, who is a composer. So I've spent much of the last 8 years building technology, and then we often work the technology that we build into musical performances, operas, small ensembles, solo performers, orchestras, and always kind of combining layers of electronics and electronically generated sounds with acoustic sounds. Along the way, I've kind of expected to get a PhD, and the area that I've been focusing this PhD on is really looking at the way that media technologies evolve and really trying to understand what the current generation of technologies mean for music in the long term, with a particular focus on looking at the internet and trying to understand what its potential is for music, and what we can do right now to make that potential stronger. So there's the direction that I think things are going to go in, and the direction that I would like to see things go in, and they're not totally opposite, but they're not totally aligned either. And so I've organized this talk into kind of 5 thoughts. And the first one is really, well, if we were going to see a big transition, if we were going to see the internet and other current generation technologies take music to a really new and a really different place, what would that look like? And, in the past, new technologies really transformed music into something completely different. And this album is probably the best example of that. So I imagine that you're familiar with this, with Sgt Peppers' Lonely Hearts Club Band. But in 1967, this really illustrates a turning point in what music is, right? This album is pretty forward thinking insofar as there's no way to perform the songs on this album live, because when they were recording it, they used all these tricks in the recording studio, like playing with the speed of the tape that they were recording to, and double tracking, and layering, and adding in sounds that wouldn't normally be considered musical. And the result is you have this sonic experience that is completely different than just capturing a musical performance. And, ever since then, that's kind of become the norm. So here's an example of how a new technology, and specifically it's the technology of analog tape and sound recording, transformed music into something totally new. Will we see that happen again with the internet? So it's hard to answer that question, but one of the ways that I chose to look at it is to really ask, how long does it take for a new medium to get to the point where it's mature and we kind of understand the language and the vocabulary of it? So if we look at the technology of recorded sound, how many years were there between the time when it started and the time when we get Sgt. Peppers? And let's look at a couple other medium as well and see how long they took to evolve. So I'm gonna share this application that I wrote, which is kind of a way to help me visualize the stages of evolution of a media technology. I was having a hard time just remembering the examples and the dates, so I said, okay, let's just lay them all out on a timeline, and we can do this so we can sort of zoom in and see a particular time with more detail. And let's just look at the very oldest surviving film, and here it is from 1888. And then let's just step through some examples of film technology and just at a very high level see how long did it take for this technology to mature, how long did it take to get to the point where it's kind of recognizable as what we think of film technology today. So then 8 years later, we start to get a stories in film. And, it's kind of hard to imagine, but at the very beginning, film, it wasn't obvious that you could use it to really tell a story. So these early films are just sort of examples of everyday activities. Like this was a very financially successful film really early on. Just pictures of workers leaving this factory after their shift. But then not too much later, we start to get these Alice G, who's pictured here, she really innovated this idea. We can use this to tell a story. And here she is in an early film called The Cabbage Fairy, where she's pulling babies out of giant cabbages. And it's...
So that's where they come from.
Yeah, right. Now you know. So some things to observe about this film is that, it's just a couple minutes long. The camera is straight on the entire time. There's no sound. But not very much later than that, we start to get longer films. We get special effects. There's still no sound that's actually recorded with the movie. But it's starting to look a little bit more recognizable. A lot of the early film work happened in France. So a whole bunch of these films are French. This is The Voyage to the Moon. Here's some brave explorers who landed on the moon for the first time, and it's notable for its special effects and, in a lot of ways, this kind of science fiction movie exists today, although it's in quite a different form. Earthrise. One of the things that we often see at the beginning of a new medium, and here this is in 1916, we see propaganda. And from looking at these media evolution timelines, to me, it looks like nearer to the beginning, we often get a lot of propaganda before the public kind of learns to understand the medium and it becomes less effective at manipulating people. But here's a British propaganda film from 1916. And this was an hour long, still no, this, you would have a live musician playing along with this to kind of give some audio accompaniment. This was very effective at convincing the public in Britain that the World War I was worth fighting.
Hey, Charles, just a quick question. When the music was played as an accompaniment, did the producer of the film have a score that was to be played, or was it random music?
That was an innovation that came later, and I don't know exactly when, but at this point, it would still be up to the performer. Yeah, but eventually we did see films that actually came with sheet music. So this is the correct music to play. So then 1926, we get Synchronized Sound. We have a feature-length film. We still don't have any speech. So then finally, color starts to become kind of available in more films in the late 1930s. It's been possible for quite a while. Here's The Wizard of Oz in 1939, 51 years after that first film that I showed. I would argue that that's the point where most of the vocabulary of filmmaking is in place. So about 50 years, I would say, in order to kind of develop the vocabulary of film. What we still don't have in The Wizard of Oz is we don't have multiple cameras that are shooting at the same time and then splicing between those cameras. That didn't happen until 1954, but much of the vocabulary is in place. And this is not to say that, nothing stopped changing, obviously, but I think it's a good indication of kind of when this medium, to me, looks pretty mature. And we can go and do the same thing with sound recording. So let's look back at Thomas Edison's first phonograph from 1877, the first device that could both record sound and play it back again. And this image of him here, that's actually his second model, so it's a little misleading, but 1877 was when he patented the first model, the first device that could record sound and play it back again. And let's just step through the timeline and kind of listen to the way the sound improved and changed as the technology changed. So this is one of the oldest surviving sound recordings, and this is actually from Alexander Bell's lab. And pretty quickly, this turned into a commercial medium for distributing music. So the noise in that recording is almost louder than the recording itself. And it was actually quite a while before that noise floor was really overcome by the technology. We see a lot of propaganda during World War II, especially. And slowly sound recording quality got better. After World War II, this technology that the Nazis had kept secret was captured by an American sound engineer. The technology was seen as sort of a spoils of war, and so it was not protected. When these tape recorders came back to America, they weren't protected by intellectual property law, and they pretty quickly spread throughout recording studios all across the country. And that's when we start to really see this transformation of the medium of sound recording turning into something really new and really different. One of the ways that it did that was with overdubbing. So prior to recording to analog tape, it really wasn't practical to make a recording and then go back and layer a second recording on top of it. And the best early example of this is How High the Moon by Les Paul and Mary Ford, who layered 12 guitar performances over 12 vocal performances to create this chart-topping hit from 1951. Oh, which I don't seem to have access to here. I need to recompile this. This will only take a second.
Charles, while you're doing that, when was magnetic tape invented and made available commercially?
So in Germany, it was available in the 30s. Prior to that, there was still reel recording. It was on wire, but early on, it wasn't really much better or more practical than recording to a wax cylinder. But it did get much better, but that was kept secret in Germany.
The wire recordings were the same technology, basically rust on a piece of wire that people were able to decode.
Right. I mean, I think the wire itself was magnetic. It wasn't that they added layers of rust like they did with the analog tape. So yeah, not as opposed to adding the iron oxide, they just used the cable itself.
Yes, magnetic wire. It was Germany, 1928.
And one of the interesting things that did enable was that you could take a magnetic reel-to-reel recorder, even a wire recorder, into a war zone and record the sound. And so that was one of the ways that, during World War I, nobody heard what the war sounded like. But in World War II, you could take one of these reel-to-reel recorders, wire reel-to-reel recorders, into a battle zone. And so it was part of that whole propaganda machine. Let's take a look here. Okay. Yes. How High the Moon. I have two versions of this application, one that I post publicly to the web and one that I use for telling the story that I'm telling now. This one has more audio that I can't publish to the web because of the copyright and so on. So anyway, 1951, How High the Moon. And I think this was really the start of this transformation. And finally, when we get to Sgt. Peppers in 1967, most of the tools that we use commonly today in popular music are in place. And they've changed quite a bit since then. But I would argue that this point, 1967, is when it really becomes irrefutable that recorded music is something completely different than live music. There's a new art form here. And so that's 90 years that elapsed between Edison's first phonograph and this kind of this album that really shows that we have something new and something different. And I would ask, okay, so about 50 years for film, about 90 years for sound recording. Let's just look and see where we are at with the internet right now. We've had global scale for computer networking for about 50 years. And, you can kind of argue about when that really started. But here, the first ARPANET node installed at UCLA in 1969. And email, TCP, a lot of things that are pretty foundational a few years after. I've looked a little more closely at the World Wide Web, which has been around for about 30 years. And I'll just share some observations about what I've found by looking at this timeline here. So we've had the World Wide Web for 30 years. The first 10 years, it looked, the kind of conventional wisdom was that the way that you were going to be successful on the internet, the way that you were going to make money on the internet was by creating content, because that was the case with radio. And there's this great essay that Bill Gates published in 1996 where he said, "Content is where I expect much of the real money to be made on the internet, just as it was in broadcasting." And over the next 10 years, very conclusively, that theory was disproven. During those next 10 years, what the conventional wisdom became was that the way that you would be successful on the internet would be by aggregating the content that others had created, user-generated content, and then advertising surrounding that. So, Facebook started in 2004, YouTube in 2005. This kind of idea of the Web 2.0 was coined in 2004, Twitter 2006, and so on. So, the first 10 years, we thought it was content. The next 10 years, we thought it was user-generated content. And then finally today, the conventional wisdom about the internet and the way that you are successful and the way that you make money on the internet is that it's not about user-generated content so much as it is about mining your users for data. And then you can use that data to make a model of what your users are going to buy or, what advertisements they're going to look at. And really, monetizing that data is the way that you're going to be successful on the internet. And of course, it's that data that has made the current advances in machine learning possible. And again, I think that we're probably in that stage of the evolution of the medium where we just see a lot of propaganda. And right now, online propaganda is really effective. So if we've had the web for 30 years and we see these three distinct changes in the commonly accepted beliefs about what it is for, to me, it looks like that things are still changing pretty quickly, and we probably shouldn't assume that the web and the internet that we have today is going to look very similar, come another 30 to 50 years.
Could I ask a question about bots making 46% of web traffic? Is that saying that bots would be the same class as video in terms of bandwidth?
I guess I don't totally understand the question. What that means is that there's software that's scraping the web and trying to convert it to data. So, and probably, that was 4 years ago. So probably by now, the amount of web traffic that is HTTP requests made by software as opposed to HTTP requests that were started by somebody using a real person using a web browser.
Okay.
Does that answer the
Yeah.
question?
Yeah, it does. I think what you're saying is transactions as opposed to actual bits transferred.
Well, yeah, I guess we should look at this report here, right? I don't actually know that off the top of my head.
Don't do it now, but
Yeah.
it's an interesting question. I mean, that thing does suggest something different than what I thought. I
Right.
thought
Oh,
the
I see.
video was swamping the web at the moment.
Yeah, that would make sense. I bet you are correct. Maybe I'll relabel that line there so it's clear. But I can also, later on I'll double check that report and see
Check
what
it
it's
out. Yeah, right.
saying.
The other 54% is pornography.
Right, probably. So I think I'm not going to go over some of these other timelines. Maybe, if we want, we can come back to this later. And just skip back to my slides here and say, so I would argue that we're still, the web is still changing. And if we want to have something that looks really transformative, that could still be in the future, although it is not guaranteed to be. I want to talk a little bit about this notion of a musical idea. And we're just going to look at a specific musical idea that was enabled by technology. And I'll come back to that concept of what I mean by a musical idea later. But we can look in the timeline and we can see these examples of musical ideas that were really made possible by technology. And there's a really great musical idea that came from the composer Karl-Heinz Stockhausen, who was a German composer, and following World War II in Europe, and especially in Germany, there was this sentiment among younger composers that everything that they knew about music had to be thrown away and you had to start totally from scratch. So you can imagine how, the Nazis invoked some of the great classical composers as sort of a way to reaffirm their ideas that something about their culture was superior to other culture. And of course, following World War II, a lot of people had to reckon that with the notion that that was actually wrong, and so a younger branch of composers said, we're going to make a totally new kind of music. It's going to throw away everything that we know about the past. And one of those composers was Karl-Heinz Stockhausen. And more successfully than anyone else at the time, Stockhausen said, we can take sounds that we've created with test equipment in a radio studio, and we can blend those sounds with acoustic sounds, and we can, the acoustic instruments that we're all familiar with, those are built on these historical ideas about what music is. With this new technology, we can use that to unlock a whole new kind of music. We can use different scales, we can use different timbres, and we're going to create something really new and really different. Here's an excerpt from this piece of music that he made using both acoustic sounds and blending them with the synthesized sounds that he made in a radio studio. So these sounds don't sound extremely similar to what we're kind of accustomed to hearing in music today, but this was a really influential idea. And that influence is evident on the cover of Sgt. Peppers, where if we look back here on the very last line, this face back here, that's actually Karl-Heinz Stockhausen, composer of Gesang der Junglinge that we just heard. The Beatles were familiar with his music and put this visual representation of the influence that he had on the album cover. Probably one place where this is really clear is if we zoom in to 1969 when they released Abbey Road. And we'll hear just the introduction to Here Comes the Sun. We'll hear this downward sweeping sine tone that, in what I think is a pretty clearly inspired by this idea that came from Stockhausen originally, but lots of people developed, using these electronically synthesized sounds and layering them with acoustic sounds. And so here in 1967, or 1969 rather, we have this clear indication of how this entered the mainstream. So that was created on a Mini-Moog synthesizer, and it's quite a bit more subtle than what Stockhausen was doing, but here it is in the mainstream. And that particular sound, that's, I hear that when I listen to the radio all the time on just tons of different music. And sometimes the reference to Here Comes the Sun is really overt. Like this album from 2005 has exactly the same thing. There's an intro with some string instruments, and then just before the vocals come in, we hear this downward sweeping sine tone. Have a listen to Soul Meets Body from 2005. So that's a little. It's a little deeper in the mix. It's mixed a little lower, so it's not quite as easy to hear. If you want, at the end, we can go back and listen to some of these examples a little bit more carefully. But there it is again, really just, almost used identically to Here Comes the Sun by the Beatles. And I just think this is interesting. 2014, Beyonce built this whole song around that downward sweeping sound. Have a listen. So today, almost all of the music that we hear on the radio does what Stockhausen was doing in 1956, which was take these synthetically generated sounds and mix them with the acoustic recordings to create something that, again, illustrates how what we have right now, the music that's common right now, is really a different thing than before the 1950s, when sound recording was really only about capturing a live musical performance.
Hey, Charles, has the mathematics of music been really discussed and the original Stockhausen experiment?
So people have gone into really great depth analyzing Stockhausen's compositions. I'll talk about this a little bit more later, but one of the things that makes that possible is Stockhausen left behind really detailed scores about how to create the music that he wrote. So if you look at the score for Gesang der Junglinge, he has all these intricate details about exactly what technology was used, and kind of, these complicated graphs in his own customized notation system that show exactly what frequency, the sound is supposed to go to, because he was not using a Western, 12-tone scale. He was using this just like specifying frequency as opposed to specifying pitch. It's interesting. You can go back and listen to the original recordings of this, of the boy who he had singing the human parts, and you can look at the score that he wrote, and the boy actually finds it very difficult to hit those pitches that aren't in the Western scale. And so sometimes, even though the notation says one frequency, the pitch that the boy actually hits is kind of sliding those frequencies onto a Western tonal system. And Stockhausen didn't notice at the time. In fact, he was kind of encouraging the boy to do this. It's really interesting. But there's so many like detailed analysis of exactly what he was trying to accomplish and what he ended up accomplishing. Like, we can look at the score with all his little notations about exactly when everything is supposed to happen. I don't know that I would describe it exactly mathematical beyond that to accomplish what he wanted to accomplish, he had to use technical ways of specifying the sound, namely frequency, as opposed to perceptual ways of specifying how it was meant to sound, namely pitch. Does that make sense? Not totally sure if that answered the question.
Yeah, I froze in the middle of it, so I'm sure you did.
Okay. Let's look at some contemporary music ideas. So if layering acoustic sounds over synthetic sounds is an influential idea from the 20th century, let's just take a look at some contemporary musical ideas. Here's one that came out of Google. If you are composing music with a neural network, it's actually pretty difficult to teach a neural network to output a musical score that contains a long-term structure. So here's an attempt based out of Google of a system that a neural network that can, this is a recurrent neural network that learns to compose music that has some semblance of a long-term structure. Let's take a listen. So it's a little bit aimless, but you can hear some structure in there. To my ear, it sounds like there are some notes that are just mistakes rather than creative blue notes. But I think that this is a valiant effort, and I do think that this is better than most of the other examples that are out there. And it's kind of one of the big areas of music research right now is teaching neural networks to create music in different ways. In this case, the music transformer generates a score. It doesn't actually generate the audio itself. So it's generating a MIDI file with the important limitation that it can't reproduce anything that you can't encode in a MIDI file, which is a very minimal symbolic transcription of a musical score. So the way that the audio that we heard was created was by just using conventional synthesis techniques, essentially a piano sample library that's then mapped onto the symbolic data about the composition. But you can also use a neural network to generate an audio waveform. And here's an example by OpenAI, what they call hip hop in the style of Kanye West. So let's have a listen to that. In this case, they taught a neural network, and specifically a variational audio encoder, to create audio waveforms.
No.
So if you know any 20th century hip hop, you'll recognize that what we're hearing is kind of a twisted version of an Eminem song. And in this case, OpenAI managed to train this neural network to generate a waveform, but what they've really done is overfit. So the network has actually learned the data set, and what we're hearing is a version of this Eminem song that the network learned, and then made that the embedded version of this learned song sound a little bit like Kanye West. So it's kind of misleading to say that this network has actually learned to generate an audio waveform, but it's still impressive that they managed to get it to sound as good as it does. So you can use all these same techniques and kind of combine them with the sort of conventional music production. You can take the audio that's generated by a neural network and layer that on top of acoustic recordings. And we'll just listen to one more example. And this is Holly Herndon, who incorporates aspects of music using technology that's similar to what the OpenAI did in the last example, and mixes that with contemporary music production techniques. Let's just have a listen to Proto from 2019. Okay, so I recommend listening to Holly Herndon's music in a dedicated way, but I'll stop there for now. That was 3 examples of kind of contemporary music ideas. And what's interesting about all of them, and much of the music that was created after Karlheinz Stockhausen's time, is that there's really no way to reproduce it if you don't have access to the original equipment that was used to make it. And finally, I'm going to talk about what I'm calling fluid music, which is sort of where I would like to see all these things go, and where the technology that I'm building right now fits into this whole picture. We can take a musical score from about 500 years ago, or even much farther than that, and we know what it is that it is trying to say. We can, with a reasonable accuracy, reproduce the music that it describes. And it's kind of surprising to me that almost all of the music that's created in the last 50 years, almost all of the popular music, you really can't do that with. If you want to go and recreate any of the musical ideas that we've heard after the time of Stockhausen, because Stockhausen was really good at documenting exactly how he made those sounds, you really, your only option is reverse engineering it from the sounds that you've heard, and then going and redoing the entire thing from scratch. And here's another example of that. Maybe you've heard this from 1971, but just listen to the first few measures of this song by The Who. If you wanted to play a cover of this song, really your only option in 2020 is to find YouTube videos of other people who kind of went through and did a bunch of digital archaeology and uncovered the process by which that sound was created. And you would use some software that looks like this to recreate it. So in a kind of surprising break from the past 500 years of music composition, right now, all of the music that we hear, whether it's created with a 20th century technology or 21st century technology, there's no practical way to share it. Really, what you have to do is take that final stereo recording and pick apart exactly how it was created and go back and do the entire thing again from scratch. So what I'd like to see is a way to take any one of these musical ideas and ship it off as a pattern that anybody else can use. Right now, if you use software that looks like this to create a piece of music and you save a file in the software, maybe 2 to 5 years later, if you want to go and open that file again, the chances of it working are extremely slim. So the half-life of a file saved by an audio workstation is very short. And the reason for this is that the operating systems change, the software itself changes, all the plugins that you used in the software to create the sounds that you're listening to changed, and there's a licensing systems where your software has to go ping some server somewhere else in the world. And the result is that when you create music that uses structured data like this, like we're seeing right now, to represent a musical composition, that there's no way to preserve kind of the DNA that created the sounds that you're listening to. So to me, it seems like we ought to be able to take any of these processes and use essentially all the same techniques that we use to collaborate and share code on the internet. So I would just say, when I was creating this application here that we've been looking at, I used 12 different software libraries for doing things like drawing vector graphics in a browser, for things like calculating the transforms that you use to zoom in and out. And in turn, those software libraries depended on 136 other software libraries that are just available for free on the internet, and I can install them all with a single command from my command line. So wouldn't it be cool if we could take any one of the musical ideas that we've heard today and encode that using just plain software, just code, and we could share those ideas amongst each other in the same way that we can when we're creating software. So could we create something that looks kind of like the GitHub, but for musical ideas? And so this is really what I've been working on for my PhD, is saying, can we build up these modules that describe musical ideas, and can we make them accessible to musicians? And this is, I'll show a demo of where this technology is right now. I haven't built a user interface for it yet, but that will come. That's often the first question that I get when I show this. Right now, all I want to be able to do is to think of a musical idea, write some code that describes that musical idea, and then allow anybody else to reuse that musical idea without having to create the entire thing from scratch themselves. So here is a video from a few months ago that I made that just shows the software in its current state. And specifically, I'm using the software to recreate the musical idea that we just heard in that example by The Who, Baba O'Reilly. So let's take a listen to this. Hello, I'm Charles Holbrow, and welcome to this demo of the Fluid Engine. The Fluid Engine is a software package for documenting, sharing, and remixing sound design techniques. For this demo, I've used the Fluid Engine API to recreate the first 16 measures of Baba O'Reilly, the 1971 song by The Who. This file shows how we set up an audio session. First, we configure a 16th note stereo delay. Then we configure a long, bright reverb. Finally, we load 2 VST synthesizer presets for our organ sound, and we send our results to the server. Let's try it out. First, we'll start the Fluid Engine server, and then we'll run our template file. We'll use the fluid save command to save an audio workstation session. Here it is, and there are the tracks that we just created, along with our VSTs and plugins. Right now, Traction Waveform is the only supported DAW, but I'll add more soon. Now we'll use the Fluid Score API to add some content. First, we'll create a mapping between single characters and timeline events, such as MIDI notes, audio files, and automation points. Next, we define a rhythm string. In this case, the rhythm maps individual characters to 64th notes. Next, we transcribe Pete Townshend's first organ part against the rhythm string on line 10. The characters in the organ transcription reference characters in the event library on line 7. The second organ part has more variation, so we transcribe it measure by measure. Now we'll send the content we just transcribed to the Fluid Engine server. We'll use the fluid play command to audition playback. My organ patch doesn't sound exactly like Pete Townshend's Lowry Berkshire Deluxe organ, but it's definitely recognizable. Next, we'll use the Fluid Score API to transform this session into a completely new piece of music. Let's add a kick drum track. We'll specify a quarter note rhythm string because we don't need 64th notes for our kick drum. We'll use the functional API to insert some automation on the low-pass filter. Syntax completion makes it easy to author sound design from code. Users who don't want to write code can still take advantage of the Fluid Engine by importing recipes that others have written already. Now we'll use a bundled library to watch our content file and send a new version to the Fluid Engine server whenever we save a change. Now I'll replace the note library for a completely different set of notes. I'm going to insert a sidechain compression pattern that is defined in a different file. If we want to see the details of the ducking script, we could use the jump to definition feature of our code editor. When we're ready, we can use the fluid save command and finish our editing in a conventional digital audio workstation. All our MIDI, automation, and audio files are still available. Alternatively, we can just ask the Fluid server to render an audio file without even going into the DAW. There are many languages for procedural sound design, like Chuck, C-Sound, and SuperCollider. Unlike these, the Fluid Engine deserializes to a DAW, supports a full programming language and not just a domain-specific language, and it was designed from the beginning for remixing and especially for sharing sound worlds. So I'll stop that there. You can see that right now, it's not complicated right now, and to me, it's surprising that this isn't possible already. Like, why is it basically that every time you want to do anything in a digital audio workstation, you're pretty much starting from scratch? I think that if we have everybody who's creating music in a digital audio workstation able to share and reuse the sound ideas that they're interested in, that could be what transforms music in the 21st century in a way that is as significant and as revolutionary as what happened in the 20th century with recording technology and analog tape. So obviously there's a long way to go before we can get there. One of the things that makes what I'm doing difficult is that we really have to meet the musicians where they are. And this was the case in the 20th century as well. So the engineering work that I showed in that video, it has to be usable from inside the tools that musicians are familiar with. And right now, that is a digital audio workstation, like we showed it. And the other languages for computational sound design really don't let you integrate into a digital audio workstation like that. When we heard that example of the Beatles reusing this idea from Karlheinz Stockhausen, one of the reasons that was accessible to them is that this technology that Stockhausen used had been packaged inside a keyboard. So you could play a synthesizer from a keyboard that looks like a piano keyboard. And that was one of the things that made that technology available to musicians in a way that made it into the mainstream. And I'll just share the long-term vision for this project with a metaphor. And oh yeah, here we go. So on the left we see this is the technology that Stockhausen used, and on the right we see the technology that the Beatles used. I think in order for something like this to catch on, you have to meet the musicians where they are already. A metaphor about where I see this going in the long term. I don't know if folks here are familiar with this game, Minecraft. But if you're not, there's this three-dimensional procedurally generated world that stretches on indefinitely, and you can build structures in it and, you know, fight enemies and meet your friends online. A world that's generated purely procedurally, whether it's a sound world or a three-dimensional video game world, what you can do is you can make it look really interesting from one particular perspective. And I think this tends to be the case with computational composition, is that the algorithms for composing music, however complicated they look good if you are only listening for one particular aspect. Maybe it's the long-term structure like it was in the Google example. Maybe it's the new timbre that was created in that example by Holly Herndon. And so here's a top-down view of a Minecraft map. If you zoom out, you start to see patterns emerge, and it doesn't look so interesting anymore. And to me, that's really what happens with computational composition right now. If you just purely rely on algorithms to generate your sounds for you or to generate your composition, is that you can write an algorithm to carefully sculpt one particular dynamic of your music, but to get an algorithm that can sculpt every part of your music, it seems like that's still a long ways off. What's amazing about Minecraft is when people go in on top of this procedurally generated world and build their own things, and we get things that look like this. And then when we have tons and tons of people sharing ideas and working together, you know, we just get an infinite number of these different, really creative, interesting, unusual worlds. And so the question that I would ask is, can we do a similar thing, but for music? So can we have everybody working together to create this set of musical ideas and all share and work with them? And that's really the long-term vision. I don't know that it's possible, but I'd like to push forward on that and see how far it can go. So that's all. thank you for listening, everyone.
And Charles, thank you.